bored.
I can tell you a joke.
No, thank you.
Knock, knock. Knock, knock.
Who's there?
Colligative properties.
Colligative properties who? Wait, what is colligative properties?
Colligative properties is when the properties of a solution rely or depend only on the ratio of the solute particles in a particular solution. They also do not depend on the nature of the solute particles. That's it, but there's more. There are actually four known classifications of colligative properties. These are vapor pressure lowering, boiling point elevation, freezing point depression, and last but not the least, the osmotic pressure. These four classifications of colligative properties have significant factors that are important to many natural phenomena and technological applications. To have a deeper knowledge and idea about colligative properties, let's elaborate them further.
Vapor pressure lowering. Vapor pressure lowering is a phenomenon that occurs when a solute is added to a solvent, reducing the solvent's vapor pressure. The addition of a non-volatile solute lowers the vapor pressure of the solvent because the solute particles occupy space at the surface of the solvent, reducing the number of solvent particles that can escape into the vapor phase. This results in a lower vapor pressure compared to the pure solvent. The extent of vapor pressure lowering is proportional to the concentration of the solute in the solution, as described by Raoult's law. This relationship is expressed as vapor pressure of the solution is the product of the mole fraction of the solute multiplied by the vapor pressure of the solvent.
Boiling point is the temperature where the vapor pressure of the liquid equals the prevailing atmospheric pressure. Boiling point elevation occurs when a solute is added to a solvent, resulting in an increase in the boiling point of the solution. Water boils at 100 degrees Celsius when its vapor pressure equals the atmospheric pressure. Remember, boiling point of the solution is always higher than the pure liquid. This means its relationship is direct. The boiling temperature elevation is determined by the number of moles of solute dissolved in the solution. Delta Tb is equal to Tb minus Tb degree, where Tb is the boiling point of the solution and Tb degree is the boiling point of the pure solvent. Delta Tb is equal to Kbm, wherein delta Tb is the change in boiling point, Kb is the molal boiling point elevation constant, depends only on the nature of solvent, and m is the molality of the solution. The formula in calculating molality is m equal to mole of solute, kilogram of solvent. The normal freezing point of a liquid is the temperature at which a liquid becomes a solid at 1 atm. Freezing point depression occurs when the addition of a solute to a solvent lowers the freezing point of the solution. This happens because of the presence of solute particles disrupts the formation of the solvent's crystal lattice structure. Remember, as solute is added to a solvent, the freezing point of the solution will be lower than the freezing point of the pure solvent without the solute. This means the relationship is inverse. Addition of a non-volatile solute to a solution lowers the freezing point of the solution relative to the pure solvent. Delta Tf is equal to Tf degree minus Tf, where Tf degree is the freezing point of the pure solvent and Tf is the freezing point of the solution. Delta Tf is equal to Kfm, wherein delta Tf is the change in freezing point, Kf is molal freezing point, depression constant, depends only on the nature of solvent, and m is the molality of the solution.
So, let us proceed to osmotic pressure. Osmotic pressure is defined as the force that prevents the flow of water through a semi-permeable membrane. It involves osmosis, the process by which solvents molecules can pass through a certain membranes, but solute particles cannot. This movement occurs from an area of a lower solute concentration to one of higher solute concentration.
We can solve for the osmotic pressure of solution using the formula pi is equal to mRT, where pi stands for osmotic pressure of solution, m for molarity of solute in a solution, R is the ideal gas constant or 0.0821 liters atm per mole Kelvin, and T is the temperature in Kelvin.
I don't get the joke.